Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we're going to look at various ways of representing the free energy, the Gibbs free energy under the aspect of temperature and pressure. And of course, we're going to look at various variations of these two specific variables and how we can be able to give that specific representation for free energy. Now, of course, we can be able to recall that from our last discussion, the concept of enthalpy can be represented by using this specific equation of E plus PV. And of course, we can be able to represent the Gibbs free energy G in terms of enthalpy minus Ts, where T is absolute temperature and S is entropy in that specific order. So therefore, we can be able to give a general equation for Gibbs free energy in terms of enthalpy, which is A plus PV minus Ts, given as such. So if we try to have a small change, perhaps in terms of the Gibbs free energy, that is going to be given in terms of dG. So we're going to consider changes in various variables of this one, or perhaps holding one constant and trying to cause a change in another. And that is going to give us an overall equation for representation of our Gibbs free energy. So therefore, the change in internal energy is going to be given, which is the first variable is going to be given as dA plus. So for the second and the third variables, we're going to hold pressure constant and change volume, and hold volume constant and change pressure in that specific respect. And therefore, see the general equation we're going to obtain from that. So holding pressure constant, we're going to have a P, and then there's going to be change in volume. And of course, we're going to have a volume change, and of course, trying to vary this aspect of pressure. And then for the third variable, we're going to have a temperature being constant, and then a change at this particular aspect of. So I'm not going to use delta, I'm going to use D. So we're going to change entropy and create the temperature to be constant, and of course try to give constant entropy and change in temperature in that specific order. So this is going to be the general equation that's going to represent the scenario for Gibbs free energy in trying to vary this aspect of temperature and pressure, and of course this last aspect of entropy that I've mentioned. Now, from the first law of thermodynamics, we have said that we can be able to give this specific small change in sigma q given as dE plus sigma W, where W is going to be a small element of work. And of course, we can be able to give this work in terms of, if it's the work of expansion, it's going to be in terms of the product of pressure and change in volume. Therefore, this last equation is going to be given in terms of a sigma Q is equivalent to dE plus P dV, which of course is going to be representing that small element of work. That of course, if we try to consider this particular process as a reversible one, we can be able to represent this change in entropy, as we said, as sigma Q over T is same as ds given as such. And of course, this therefore is going to have an implication that we can be able to represent sigma Q as a product over T ds given as such. Now, considering this specific case, of course, this is going to be our equivalent to this specific case. We can be able to, of course, I'm just going to okay. This is specific T ds. Okay, this is that's correct. So if we try to look at this and this one from the first law of thermodynamics, which is of course going to consider the pressure, of course the pressure over the system, whereby we are given as sigma q over t. We can be able to give this specific version of the equation. Let's call this one equation 1. We can be able to give a version of equation 1 in terms of a q sigma q, and of course this is going to be in terms of a tds, whereby we're going to have a t ds is equivalent to dE plus PV given as such. So let's call this one our equation 2. So therefore, from this particular equation 2, we can be able to consider it in this overall equation let's call this one our equation 3, because it was the first equation that we developed, but I'm just going to give this one for the sake of our clarity. So if you try to consider this specific aspect of equation 2 and 3, we can be able to look at various elements of equation 2, which are of course being shown in this specific part of equation 3. And of course these are going to be DE and PDV, whereby this is DE and PDE. So the first two sets or all elements of this specific equation are going to imply TDS, which I'm going to do this away with this one, so that since it has assisted us reach at this specific point. So the overall implication of this is that the delta T can be given in terms of a TDS, which is a TDS, which is a constant temperature and change of course in entropy, and therefore plus VdP at this specific point, and then minus TDS minus SDT given as such. So this is going to form our equation number 4, and of course this is going to be a result of this specific evaluation that I've given above. So we had said that we can be able to give this specific section for STD, and of course this is going to be from this. So we're going to employ the concept of algebra in trying to do a simplification of this specific equation. If we try to look at this first term and this one, they are going to be like terms but opposite in terms of the signs. So TDS minus TDS is going to cancel this one out. So we're going to have another version of our equation number 4. So I'm going to do away with this so that we have this specific space for discussing that. So we're going to have a DT represented in terms of VdP, and then minus SDT, which are going to be the two variables remaining from that specific evaluation. So of course this is going to be representing the general case for the change in Gibbs free energy using that specific equation. So at constant pressure, we are going to see that we can be able to represent this particular version of the equation, whereby the dP at constant pressure, dP is going to be equivalent to 0. Therefore, the Gibbs energy at constant pressure can be given in terms of a dT and then negative SDT given as such. So on the other hand, we can be able to represent this particular equation at constant temperature. And of course, this is a consideration for constant pressure, of course, which is going to give us equation perhaps number 5. And if we consider the case of a constant temperature, then therefore we can be able to give this version of the equation using the aspect of a volume, which is going to be given in terms of a Gibbs free energy over T over pressure. So this is going to be pressure at constant volume given as such. So basically, this is going to be the implication of this specific equation that we had written for volume. I'm just trying to check that one from. So that is correct. So if we try to consider this one at constant pressure, then therefore from this version of the equation, we're going to see that this is going to be dP is going to be equivalent to 0. Therefore, we're going to have Vt represented as dG, Gibbs free, changing Gibbs free energy is negative SdT given as such. And at constant, of course, temperature, we're going to see that this second element of the equation is going to be disappear, and therefore we're going to have VdP is equivalent to dG. Dividing by dP, of course, is going to give us this particular representation for volume. And if there's going to be a change taking place between P1 and P2, that's a variation of pressure, we can be able to represent this overall equation for a change in pressure using this specific equation. So from this, we can be able to, of course, perform a representation for changing in Gibbs energy using the aspects of pressure, whereby we're going to have dG, the integral of a dG between G1 and G2 is equivalent to the integral between P1 P2, which is going to give us V dP. And of course, we had said that this is going to be taking place, of course, under constant temperature. So we have folded the temperature constant, the second aspect or the second element of this specific equation on the right side. it's going to disappear, and we have VDP given as such. So we're going to perform an integral part of this using pressure 1 and pressure 2 given as such. Therefore, the change in Gibbs energy, which is delta T, is going to be given as T2 minus T1 from this specific integral, which is going to be represented as P1, P2, and then we're going to have a VDP given as such. So, so as we said, we can be able to give various variations of this specific representation for free energy using temperature and, of course, pressures we have said. And we can consider the case of course, the concept of so for a constant temperature, we can consider the case of perhaps a single mole, whereby we said that the mole is going to be represented by n. So this is going to be 1 mole. N is going to represent the mass, but the value of n is going to be equivalent to 1 in this particular case. So therefore, considering that specific aspect and constant, of course, temperature, we can be able to give a variation of this specific equation by considering that 1 mole, whereby we say that from the ideal gas equation, PV, just give it in a more elaborate way. So PV is equivalent to nRT, whereby we say the value of n is equivalent to 1. Therefore, we can be able to give a volume, which is this one, in terms of RT over P. And we're doing a substitution for this particular equation. We're going to have the Gibbs free energy given in terms of RT, of course, which is volume from P1 to P2 over this specific PP over P given as such. So this is going to be the version of the equation we're going to obtain for considering this specific aspect of 1 mole. And of course, this is going to be, from the evaluation, it's going to give us RT, the natural log of P2 minus P1 given as such. So this is going to be the representation of our Gibbs free energy when we're going to consider the case of a constant temperature about a variation in pressure, even in that specific version. So as we've been discussing from various aspects of this specific video, we have seen how we can be able to do various variations of our temperature and pressure, and the various, of course, the equations that we can use to represent the free energy, especially the Gibbs free energy in various forms using various variations of these two specific aspects. So catch us in our next video as we're going to look at the different aspects of this particular form of free energy. And of course, that is going to assist us in evaluate various equation sets that we may come across in our discussion. So that is it for now, guys. Bye. God bless you. Catch us in our next video.